lecture on the chemical reaction engineering. I'm Dr. Sabri. This is for the subject of Introduction to Chemical Engineering. The objective of this second lecture is on the reactor design and the mole balance equation. Upon the completion of this chapter, you should be able to first describe the concepts of reactor design and explain how material balance of reactor is determined. Reactor technology is several. So basically it is conducted in batch mode and continuous mode. This is the slide from the previous lecture. Batch reactor will be in the tank form. Continuous can be into tank reactor or tubular reactor. Under the tubular reactor, there will be a blank tube, which is called plug flow reactor, or in short, it is called plug flow PFR. And it can also have a catalyst inside, so we call it fixed bed reactor or packed bed reactor. The size of the reactor can be bench scale, where we just use glassware like beaker or flask to run the reaction in the lab. So the size probably around 50 milliliter to 5 liter. For pilot scale, it will be between 5 liter to 50 liter. So the purpose of using pilot scale is to study on the mixing and mass transfer limitation to the reaction. Finally, it will be industrial scale, depending on the size of production. So the size will be so big for a particular production. For batch reactor, these are illustration for the batch reactor. This is one example of industrial scale reactor. This is also industrial scale reactor in the waste treatment system. This glass lab scale. This is a pilot scale. The size will be around 5 liter and 6 liter. And this is the lab scale of batch reactor. So before we determine or calculate the mole balance, there are some assumptions made to simplify the calculation. First, for batch reactor, it is run under unsteady state operation, meaning we vary the time so that we can achieve the desired conversion. How much the reactant will be consumed depends on the time used to run the reaction. Second characteristic is there is no difference in concentration and temperature. We assume the mixing is perfect. In your in the beginning of this topic for the basic of reactor design, mainly used for small scale operation like in the lab, suitable for slow reactions, for example wastewater treatment, and mainly used for, but not exclusively used for liquid phase reaction. Many batch reactor is used for liquid phase reaction, just probably very few for gas phase reaction. One example of the gas phase reaction is combustion engine. So the explosion of complex oxidation occur in particular time, so it is considered as batch reactor. Next is the continuous step tank reactor. This is called CSTR. It also called back mix reactor because the name comes from the tubular reactor that we modify so that it will behave like CSTR. This line this line is important to dilute the feed. The characteristic of the CSTR, it will have low concentration of feed. So normally we have back mix flow like this to dilute the feed. This is due to the selectivity issue of the reaction normally. So we normally have steady state operation. There is no change in time, not like batch reactor. The change of concentration within the time is not is zero. The reactor is normally used in series from one CSTR to another CSTR. It will be arranged or will be sequenced in series. There is no difference in concentration and temperature. Similar to the batch reactor, we assume the mixing is perfect and normally used for liquid phase reaction. And normally, in fact, it's suitable for viscous liquid because it has stirrer. We use stirrer to mix and well the reaction mixture. Next is the tubular reactor. This is illustration of the tubular reactor. This is industrial scale, pilot scale, and lab scale. It is also steady state operation. We don't determine mole balance for unsteady state operation. For undergraduate, normally we just ask the student to calculate the steady state operation. But since this is the introduction, so you are not going to calculate anything for the mole balance. Next is there is no difference in radial, but there is difference in axial direction. Axial direction means throughout the length of the tubular reactor, the concentration of reactant will decrease gradually according to the rate of the reaction. So, and this flow reactor is suitable for fast reaction, mainly used for gas phase reaction. And temperature control might be difficult because of the aggressive reaction. And there is no moving part like tank reactor, and there is no stirrer inside the tube. Next will be the mole balance. How the mole balance of the reactor will be determined or will be derived. This is general equation of reactor or unit operation in reaction in chemical engineering. It has input, output, generation, and summary in the form of differential equation, whether J change with time or not. So for batch reactor, the spatial variation is due to the time of the reaction. How long you run the reactor, that will determine how much reactant is consumed and to form the product. There is no feed or flow in entering the reactor because it is batch reactor, and there is also no exiting flow or output flow. So the equation of mole balance only from the generation and the DNJDT. As we also know that the generation for reactor or reaction is the multiplication R times V, where the unit of rate will be mole per liter per second times the volume will be mole per second. So this is the flow rate of unit component. From the ODE or differential term for J, the NJDT, we can get this equation. RJV equals to dNJDT, and we can calculate T because T is actually design variable for reactor. It will determine how much we got to calculate T to determine how much concentration of J will decrease. How much J is consumed in the reactor depends on how long the residence time. We call it residence time here. This is residence time for the reactor, and this is how we calculate the time. Next is the CSTR. CSTR at steady state, similar general equation for reactor. Fj0 minus Fj plus Gj and the NJDT. So the NJDT equals to 0 because it runs under steady state mode, and thus the mole balance will only be from the flow rate and generation, and simplified into this simple algebraic equation where V equals to Fj0 minus Fj per negative Rj. We can change this equation into the function of concentration. So Fj equals to Cj times mu. This is volumetric flow rate. So Cj is in the unit of mole per liter. Mu is in the unit of mole per second, for example. So the unit of F will become mole per second. The volume will be volume of the reactor will be the design variable. The design volume will be design variable for CSTR. It will determine how much conversion of J can be obtained from the size. So the size will determine how much conversion of J. We can calculate V by setting up how much the final J concentration or conversion. Next is on the mole balance of PFR. This is illustration of PFR. Inlet is Fj0, outlet is Fj. There is change of G due to the change of V. Start with general mole balance of unit operation. For the reactor, it will be Gj. At steady state, the NJDT equals to 0, and change of J throughout the length of the reactor will be this form, and G is actually Rj times delta V. So we can simplify this into this equation, and take a limit into delta V equals to 0. So you have ODE, ordinary differential equation, for the mole balance of the plug flow reactor. So similar to the batch reactor, but different different variable. Where here we the ODE or the differential form is in the flow rate and volume. So the volume is again the design variable of the plug flow reactor. It will use to find out how much conversion of J in the reactor. This is common. In general, we have three types of variable. One variable is constant. Second variable is manipulative variable, or in this case it is V. So manipulative variable in engineering is design variable. In this case it is V. And the third variable will be the response variable. Response variable is the variable that will be affected by the manipulative variable that you play around. So the V is design variable or manipulative variable, and Fj will be the response variable. So V equals, you can write in the differential form, and you can also write in algebraic form, where we find out V from this integral. Similarly for the PR, so we just substitute V with W, which is weight of catalyst, and the rate will have a prime symbol here to differentiate between non-catalytic reaction and catalytic reaction. So this is the equation, more or less similar to the part for vector. Difference only the width of catalyst and the rate symbol. In summary, these are equations involved in vector mole balance. So as you can see here, there are 1, 2, 3 ODE or differential term or equation for batch vector, PFR and PBR. On the other hand, you will have simple algebraic straightforward equation to determine the design variable of set start, which is volume. So the ODE can be changed into integral form. The denominator will be the design variable. For batch vector, it is t. So we can convert the ODE to integral, where the t the subject will be the design variable of the vector. So PFR here is v, and PBR here is w. All these variable will be variable to the variable of design will be the design variable for the vector. That's all for now. See you in the next lecture. Bye bye. Assalamualaikum.